I'm Don Dennison, and this is a talk on machine learning and deep learning. Here's a little bit about my background. A couple things before I start talking about this topic, which is a fairly complex topic. I don't consider myself an expert in this in any way. There's a lot of people who are doing a lot of great talks on the actual science and technology behind this. But I do understand a fair bit about medical imaging, and I spend some time, always keeping my eye open for things like disruptive and innovative technology trends. So I'm hoping that this talk will really provide an overview of the technology and maybe even more so the cultural implications. And I'm hoping that this can be generally appreciated by most people. So first, let's try to define what is machine learning and deep learning, and even more importantly, what do they mean for humanity? So let's take a look at a couple sources. So if we look at Hollywood and what their vision of it is, when machines start to learn, the plot usually reveals that things don't go so well for humans. But if we look at even pragmatic scientists and innovators have made public statements in terms of the, what this could mean, and these are kind of a doomsday kind of comments, what this could mean for humanity and humans in general. So that tells you there's something fairly game-changing about this type of approach. And if we look at gamers such as the high-profile Watson defeating the Jeopardy champion, and more recently Google's DeepMind defeating the Go champion, which is considered one of the hardest games for computers to learn. But what do we mean by it really? It's really I won't read this exactly, but it's a subfield that uses pattern recognition, artificial intelligence, and a lot of the technical theory behind this has evolved very rapidly over the last little while. But fundamentally, think of it like where typical software, you program it to do the same thing exactly the same way. It's considered performing properly. If it does the exact same thing every time when it gets the same inputs, it should have exactly the same outputs. But machine learning is software programmed in a way that looks at the patterns of things and tries to determine what it might be the more correct output or the more important finding than just simply what it was programmed algorithmically to do. So we use a lot of terms, and we may be in an era of jargon around this kind of topic, but the question is, isn't artificial intelligence and machine learning the same thing? There's a number of links you'll see through this talk at the bottom that give you references to some of these great discussions around this type of thing. And here's one that basically talks about machine learning is really the only kind of artificial intelligence there is. And this is one quote that I thought was quite interesting. It says, "We made more progress in 3 years than we've done in the last 25 years." And it talks about image understanding, voice understanding, and text understanding. So I've highlighted those because obviously in healthcare, and more specifically medical imaging informatics, one can understand why those type of capabilities would be very, very interesting to our domain. So just as a provocative question, when we take a look at what can machines do, and I wrote a blog post in 2013, and for those people who understand something about fantasy sports, I participate in a fantasy football league. And what was interesting is that every week after the games were completed, I either won or I lost that week in a head-to-head competition. But what was interesting is that it would generate this extremely detailed report about how my team fared against the other team. It cited decisions I made in terms of who to start, whether it was good or not, whether I was smarter than the advisors, all that type of stuff. But if you imagine, there are literally millions of these leagues out there and teams with billions of permutations. There's no way humans can write this, but a robot was able to put together a very human readable, insightful article on this mostly useless event. But it had all the facts, like the outcome was known, the statistics were known, and it knew how to put together this discussion. So here's an example. If the rudimentary quantitative findings are available, then, and it understands what the purpose of a document is or communication is, robots are very good at taking that kind of human language and putting it around these things, structuring it away and highlighting it. So the question is can image finding extraction and EMR data provide this data necessary to produce this kind of report? That's a question we'll come back to. So another question, can a machine learn to teach? This is an article that came out recently. You'll find many of the references are quite recent because this is one of the hottest topics being discussed in technical journalism. Everybody's looking for every domain these days to see how machine learning is affecting it. But this one was interesting. It was basically a test where they had one of the TAs, or the teaching assistants, was a robot and trained to essentially help students with their questions. And it wasn't revealed to them. Several were human, one was a computer. It wasn't revealed to them till later, and many of the people who were participating were completely unaware that it was a robot, and in fact, one of them even thought it was the best TA that they had, mostly due to the responsiveness, because obviously a computer can reply very, very quickly compared to people who have other things to do. So this one I found interesting. If we look at all the different professions and domains, someone took a neural network and which apparently named itself Benjamin, and they fed in just a bunch of scripts from things like Highlander and Game and Ghostbusters, and it produced a movie script, and they actually shot the movie, just for interest. And apparently, this is to date, this type of technology is not yet a threat to script writers or screenwriters, but I can imagine that given, if you took a look at, what caused people to react to certain movies emotionally, excitement, fear, intrigue, suspense, all those things, and you can start to measure those things, it could be very easy for these type of things, these type of algorithms to start to assess. So if somebody says, hey, I've written a script for this next movie, it would be very easy, rather than having everybody read through it and form their own opinion, it could say, okay, this scores on this kind of level for appealing to, demographic like this who are looking for horror movies, and it contains the elements, this type of thing. So it may start off as kind of a script reviewer, and eventually may learn to actually how to put this stuff together. And certainly we've all seen movies that certainly felt like a computer churned it out. So this was an interesting thing that happened recently. Microsoft produced an AI bot on Twitter, and essentially it was learning what was important, what to say, based on things that were being tweeted to it. And this is a interesting thing. It was essentially, after 24 hours, it based on all the terrible things that were floating around the Twitterverse, it learned to become a very horrible person, which is simply reflecting perhaps some of the low quality information that's floating around Twitter. But there's an interesting thing, and this goes to the point of robots will learn, but if they're provided wrong information or wrong examples, they will learn bad things. So obviously, ethics is going to be a big part of the discussion as to the evolution of this type of technology, and where are the controls in place to prevent the software from doing harm to humanity and actually continually learning for ways to help humanity, which obviously is, you see in science fiction a lot. So when we talk about deep learning, what is deep learning? It's essentially a branch of machine learning that uses a set of layered algorithms, and there's a number of talks that are out and some that are coming up through programs put on by organizations like SIM that really go into the technical detail of this. But think of this as, usually when people are talking about analyzing images, for example, that's usually using a deep learning methodology. Here's an example of where images were used to, a specific type of deep learning was used to analyze images to determine, can it detect images that contain a specific celebrity. So, and it goes through all these different layers of algorithms and weighting of measurements. And so one can imagine this is, okay, if it can measure a face, which could be taken from different angles, different lighting, different hairstyles, everything, and the variability of characteristics, how hard would it be for it to determine something else in imaging, such as a tumor or some form of an anatomical inconsistency? So what can machine and deep learning actually do? So if we take a look at how efficient, how companies are learning to use machine learning to become more efficient, there's a lot of study. If you read some of these things, obvious areas are in areas of customer relationship management, looking at patterns of how customers buy or don't buy or those type of things. But if we look at some of the areas, this particular article talks about areas where they're starting to get some maturity is around previewing video, and I've highlighted too there interpreting images and documenting and data entry. And then there's some other items there, but I highlighted those because obviously within medical imaging and medicine in general, interpreting images and documenting data entry is a lot of what we do. So who's working on it? This is a example of some of the companies. You can see the company that came from there. I think what you'll find is that during this type of phase where companies are, everybody's getting into this in some way, that there's going to be a lot of startups. You're going to start to find those getting bought up. You're going to start to find people who are claiming to be in this game but are only peripherally using some form of machine learning. They may be using more traditional methods. But I think we're in that kind of heyday where it's kind of, 1,000 flowers blooming kind of thing, and some will survive and some won't. So to that point, you can see there was one of the more notable companies in this space, MetaMind, was purchased. There was read one article that talked about highlighting this as one of the more interesting companies and products that were coming out, and within a week or two they were acquired and then retasked to focus on what Salesforce is interested in. So let's ask some questions. There's a lot of discussion on machine learning. It's getting a lot of discussion, and it's in a lot of the press, and obviously I'm doing this talk and other people are doing talks on it. I love the Gartner hype cycle because, if you've been in this game long enough, you've been around long enough, you'll see there's always something that's being hyped. And in my opinion, this hype cycle proves itself over and over again in the fact that you get this phase where people believe that this thing is going to change everything, whether it was smartphones or 3D printing or whatever it is. And then there's when it actually starts to go into application, smart cars, which is using machine learning, the self-driving cars, there's all this hype that this is going to be happening, and then of course we start to learn exactly how hard the problem is, and it takes a lot of effort to bring it across to be reliable enough for general consumer, general professional use. So I think right now, if you take a look at this from a little less than a year ago, it really, you see we're on the right hand side. So we're about to go on this fun roller coaster down into the trough of disillusionment. But let's take a look at some of the ways to think about this. And again, this is kind of the way my brain works, and I break things down visually. So we have kind of this management layer, which is storing all of this data. So things that store structured text, like our electronic medical records or clinical data repositories, or aggregated databases like health information exchanges. We have images that are captured, such as things that are stored in enterprise content management. It might be a document with scanned text. It might be a VNA with diagnostic images or clinical images. We have DICOM images, which are being stored, which contains not only the images themselves, but important information like radiation dose in structured format, structured measurements in DICOM SR. We have all kinds of pathology and genomic data being recorded. And we have these kind of standard atlases that we can compare things against, like ontologies and knowledge bases. So all that data is there. And if you take a look at the bottom, in order for any of that stuff to be available to us and for us to make use of it, we need a few things to happen. And what's interesting in terms of why is this being discussed now, I believe, is the vector that there is a number of independent things happening in parallel. So for example, the big push of digitizing patient records, right? So we took film and made it filmless, for some time now. But the adoption of EMRs, shifting all of this stuff into EMRs and getting all that paper put into the EMR, and as I show here, this potential for optical character recognition, or OCR, to take that scanned documents from 10 years ago, extract that information, and actually start to process it using NLP or natural language processing and indexing it against an ontology as shown on the right, you start to get this stuff that was inaccessible to being accessible and viewable by humans, processed but through one set of processes to where it's actually indexed and cross-indexed to meaningful uh, concepts using other technologies which are evolving. And now we start to have structured data that has been in existence for 10 years but in a filing cabinet, and now we can make use of some of this information. The other thing that's happening is through this push towards consolidated enterprises, or even within a single hospital, is driven mostly from IT cost control and record access, is this whole consolidation of all this data. So 10 hospitals, each with their own EMR, all getting into the same health system and rolling out one big EMR. 10 hospitals with 10 PACS, all putting that data into one VNA or consolidating on a single shared PACS. We now have fewer systems we have to get data from, and generally when you get to fewer systems you have a little more consistency of that data, so it lowers the effort to kind of get access to that data and pull it out. We have health systems embarking on enterprise imaging, so now we're getting things like dermatology information and scope information and wound care information, and all this stuff is coming in, as well as ongoing programs as part of EMR adoption of scanning all this back office documents and getting it all available within the record. And on the front end, we have better and better modality clarity, better and better camera resolution and quality of those things, and those images are being started to cross-index and consolidated into these repositories. And in addition to that, in these consolidated enterprises who have often operated as separate and distinct entities, separate hospitals with their own patient ID, also known as an MRN domain, now we're starting to get things like EMPIs as part of the EMR or part of the jurisdiction to cross-index all that. So now, not only am I starting to get on the verge of, in many organizations, of having access to all clinical data, all scanned document information, hopefully indexed by optical character recognition so I can do full text searches on it, plus all diagnostic imaging across all different domains, cardiology, radiology, everything, enterprise imaging that's coming in, and all that clinical data coalescing together. I now have techniques to say, regardless of which point of service or which facility across this entire enterprise, I can now tell one patient and cut through all of that, where before I'd have to talk to 10 different hospitals and try to piece those together. Why is that important? Well, that gives us access for a given patient. So much more about them is known. So much more now is coded and structured. So when we start to want to learn and apply that learning to a given patient, we actually know much more about the actual subject we're talking about. So on the front end, on the top there, I'll just touch on is the data entry. So we have all this people entering information into the EMR OCS, eventually wearables and patient entered information and all kinds of other sensor information going through smartphones up into these systems. And then we have this visualization where the EMR obviously has its own user interface. We have image viewers, like enterprise viewers, that can be embedded within that or accessed independently. And we also have these like specialty clinical applications that are very purposeful. So potentially for specific types of disease, if we imagine we have all of this data as I've described, and it's cross-indexed by patient identities and cross-indexed by all the different contexts and content that is now available digitally, to compose a very specific application that's pulling all that data real time and presenting it and analyzing it, this creates a new opportunity for highly specialized, highly personalized medicine that rather than a general purpose EMR screen and a general purpose radiology PACS, you now have an application that's highly tailored towards that particular patient and their particular disease instance. So I think that's an area of you're going to see of innovation, because the cost of producing that, if I don't have to build a system that has to go and collect all that data, it can just pull it on demand, is far, far lower. And that will shift the amount of resources available to that visualization and that context cross-indexing to be available. And I think there's going to be a lot of stuff in terms of cross-indexing findings from genomic data and pathology data outputs into that clinical application. And obviously, the big area that everybody's talking about are these algorithms that actually help you take sets of input images and use that learning from what it's learned from looking at prior images and extract out meaningful findings and being able to quantify those. So size, density, progression over time, location, and then cross-index that against all kinds of statistical data for patients of similar genetic makeup or gender, age, etc. So that was a long slide, but let's talk a little bit about why now. Like, why is this happening now? First of all, the processing speed. This work, for those of you who don't know a lot about computing, it's big amounts of data. It takes a long time. What may have taken weeks or months a short time ago, the advancement of CPUs and more particularly graphic processing units, GPUs, produced by some of the leaders in that area, allow us to do things in minutes or hours that would have taken much longer. So we can, in other words, the brain is faster, we can learn faster, and it's now, we can then apply those learnings and feed it back into the system so we can progress much faster. So essentially think of our cars are now 10 times faster than they used to be. The quality of the image is going, and if you compare, say, a CT image or MRI or even breast imaging 10 years ago versus today, there is a number of advancements in terms of improving that quality. So it helps these algorithms will, what may have been difficult to characterize previously is now much easier to characterize. All of that information I talked about in the prior slide is now digital. It's available. In many cases, it's accessible through an API. Advances in things like HL7 Fire, which is a new standard for using web methods called REST APIs to real-time pull just the information about records and resources that you want about a patient on demand, and the equivalent in imaging called DICOM Web, which is a DICOM standard. Those kind of watershed transformational capabilities that are now becoming standardized and are showing up in commercial products allow us this ecosystem accessible of historic data for learning and current patient data for application of that learning. And it's all being aggregated. Yes, it's easy enough to make, I shouldn't say it's easy enough, it's feasible to make things interoperable, but if I got to query 1,000 databases to find out about a patient, that's simply inefficient. And the more of these consolidated enterprises and aggregation inside the enterprise or outside the enterprise is becoming a real asset. And of course, the algorithm that's going to develop and take all of these other factors into account so that it can advance. But the other thing is, it's easy enough to create computers, and as we've seen from the Hollywood examples, if nobody wants it, it doesn't matter if it exists. And what's happening now, if you think about it, and I've had conversations with people of different generations, is the generation, especially the one that's coming up, has an enormous amount of trust in computers. So you've all heard stories about somebody on their smartphone with a GPS that tells them to drive off a road, and they end up in a field and they do it anyways. You know, if your passenger told you to do that, you would say no, but because your smartphone said yes, do it, people did it. People of this era are starting in generation have enormous amount of trust in their computers to tell them where to be, what is the truth about something, where they get their information. So I think that people over time will start to see other examples and start to, from a cultural point of view, they will begin to accept that computers can give them advice and they will trust it and make life choices over it. The other one is obviously the huge pressure of controlling the cost of healthcare. If there are, you know, expensive but low sophistication tasks that can be automated, we always look for those. And if machine learning can help us find those and help us come up with solutions for them quicker, there'll be great interest in them, not only by the consumers, such as patients, and by providers, such as doctors, who don't want to do these repetitive, low sophistication tasks. There will certainly be interest by payers, including government. So those things lead to what I believe is a societal and cultural acceptance. We're going to be, if I'm forced to choose between going bankrupt from the cost of doing healthcare one way, taking a traditional healthcare model, or putting more faith into computers and not going bankrupt, I can tell you, I will be, I'll feel great pressure to accept it, and I think that societal acceptance will start to come. And I think that there'll be a lot of forces from the payer side, from the vendor side, and on a competitive provider side to tell the story and try to change those attitudes towards this. You see that in other areas of machine learning, such as self-driving cars and other areas. So between what's happening in the bottom in terms of scientific development and capabilities in terms of IT infrastructure and availability of data, And on the top, those kind of trends and vectors of how we are changing our attitudes towards computers and obviously the crippling cost of healthcare for many people. This is what the definition of an application is: applying a set of tools to a problem. Uh, and that's where those things will converge and evolve. So uh, what what might machine learning and deep learning and what that might mean to radiology and how might it affect that? So I have this concept of a couple of different paths that I think this will evolve to. And this might be a little controversial for some, but I think you'll find that it's probably realistic that these are with some variation, two of the primary strategies will happen. First of all, on one side, you're going to see a certain group of researchers or vendors or advocates who are going to basically look to use machine learning and deep learning to enhance and advance the practice of radiology. And this is essentially, they're going to say, provide tools that automate a lot of the stuff that RADs or other support staff have to do, and they're going to cooperate with the radiology establishment. They are going to go to the societies and the colleges and the subject matter experts and going to participate with them to validate this and advance this and to get their buy-in and to look at where does this technique fit into the entire chain of the patient care, including the diagnostic areas. On the other side, this would be a little more of a competitive approach, which says, okay, these physicians, what the task they're doing is something I believe technology can do better at a lower cost with the same or equal or better degree of quality and reliability in terms of the conclusion it comes up with and what it recommends. And so a lot of the people who will concern themselves with machine learning and deep learning, they'll be talking about the type of applications on the right-hand side. The people who are strong advocates, they are generally speaking about applications or strategies from vendors on the left-hand side. So who's going to support what? If you take a look at some of the messaging from some of the leading vendors in this area, they will look for allies that on the consumer side, they will appeal to patients that perceive radiologists as valuable care providers. Allies will be imaging vendors who are in the industry today, so modality vendors, PACS vendors, those type of things, because those companies still play a role. They still are selling their products into the establishment and the established structure of the organizations, departments, those type of things. And you'll also find values in physicians that value radiology's contribution. They like their radiologists. They interact with them. They see value in that communication, and maybe even some of the regulatory bodies, because obviously they've established their entire process and structure around a definition of a lot of their guidelines based on the current state today, and it's much easier for them to use a very similar approach, at least, even though the technology may be very different, but their approach of risk assessment and impact and risk to operators and patients a lot of those same kind of lenses can be used in this. So they probably will see, I'm going to guess, we'll see this on that side. So on the other side, who wants to blow the system up? Well, you may find patients who have had perhaps a bad experience with a healthcare system that's they found ineffective or too expensive. And if you have patients and consumers that perceive radiologists or even doctors in general as error prone, if they view them as motivated by money, they will be all for having computers put those people out of work, or at least some of them. I think you'll find IT vendors that are really selling more, not perhaps healthcare medical device systems, but more general and consumer IT vendors, people who are providing smartphones or apps directly to the consumer, wearables, those type of people. They will be quite interested in seeing where this type of technology, which is what they're using in a lot of other areas of their business, can be applied to healthcare rather than complying with the existing models we use. And if you have physicians that actually don't like radiology or don't like radiologist contribution, maybe they have a reading group that doesn't provide good service, or they just in their general subspecialty they have a for whatever reason don't respect what radiologists do and the contribution their report provides, they may be more than happy to see that specialty domain be affected negatively. And maybe the payers, if the payers get to a point where they can actually see that in areas that machine learning and deep learning can get similar or better outcomes at a great cost savings, they, I think, will be quite motivated by that, and they will obviously have a lot of pressure to find ways of using that technology so that they can lower premiums to be competitive with their other payers. So it'll be interesting to see how that vets out. But there's a few other things that I'll touch on. One is there's a number of technologies and toolkits. This is another thing that's affecting it, is people who are getting into this area, they don't have to start from scratch. There is a number of very rapidly maturing toolkits which allows um, researchers and developers and program developers to start with a toolkit and basically start to apply this much more quickly to their problem domain. So there's one here that Google has put out, and just within June 2016, they also made it available for iOS. There's also Amazon is joining in. So basically a lot of these large-scale uh, IT enterprises have been using machine learning techniques internally and developing platforms internally, and some of them are now packaging those up and making those available and supporting these for external use, which is a very interesting um, kind of a threshold where now it's not as hard for people who have the aptitude and the interest in this area. It's not the barrier of starting it. You don't have to have an enormous budget for this type of thing. So there's a couple of companies. Here's one here I've listed here. I'm sure there's others, and I've got some links here that talk a bit about how some of these have a vision, how some of these organizations have a vision of how specifically deep learning can be applied to radiology. You could take a look at that and judge for yourself as to how applicable it is. So I've got a few closing thoughts. As I look at this and I'm trying to predict where it's going to go, which is what I like to do. I've been trying to think about what are the forms of the outputs this is going to take. So obviously, when today the standard is if I generate a report, it generates a document structure that gets communicated from the department to the EMR, typically in what we call an HL7 ORU message. That's well known, well understood, and millions of these things are flowing around every day. So is that the form that this is going to take? Because that's kind of our mental model of it. Or is this going to actually produce a bunch of discrete structured information, including pulling out images that have information in them, or subparts of images that show just that lesion or that fracture or that bleed or whatever the issue is, and compose those as a collection of linked attributes, which then get presented in whatever form is best for that consumer. So how I'm presenting it to the general practitioner who's sitting in the room with the patient might be different than how I'm presenting that data to the oncologist or the trauma surgeon. So it can vary quite a bit. Today, you get this narrative report out of radiology, and there's a lot of push to switch that to structured so that we can code it a little better, but still it's going to be coded and structured within a document concept. I'm wondering whether these computers will think that coarsely, or they will think much more granularly as just a whole bunch of arrays of data. And where will that be stored? Are we going to put that in the EMR, which means we have to figure out, okay, what schema does the EMR understand that we have to then map that into and link it to a patient? Are we going to take some of that structured data of findings that are being presented within those images and put that back as some form of structured information, like a doc MSR, back down to the images, so it exists with those imaging records linked to within that exact diagnostic study? Are we going to extract that out and put those into regional or national data warehouses and registries that are disease specific or technique specific or anatomy specific? Where is all that data going to go, and who is going to own that warehouse? Is it going to be national groups and societies within a specific domain, or will be more consumer-driven registries like we see with, say, for example, Google can store all kinds of data, and they often do that for no cost or low cost. So where will that data end up going, or how many places? And how are we going to actually visualize this? So we have all these findings and measurements and tracking and time and compared against statistics and cross-reference against all these different ontologies. how is that actually going to be presented out to the various stakeholders? Is it going to be presented kind of like a CAD marker where you look at the images and it's saying, hey, looky here? Or is it going to be a composition of a dynamically composed into a multimedia document with even dynamic imaging that's, cardiac imaging that's right in the middle of the page, and structured data that links to normative values or can, hyperlink out to generate dynamic reports or structured graphs? What is that all going to look like, and how does that app get delivered on whatever you need it onto, whether it be tablet device, a phone, a desktop, who knows? And who needs to be involved, or who should be involved in terms of defining this stuff? We've traditionally had a lot of success and put a lot of faith in HL7 a lot for the clinical structured data, DICOM a lot for the imaging data with its structured information model. Is there some other standard body that should be defining how we are going to persist this? Are we going to try to map this new sets of discrete data into these existing models, or are these standards bodies going to evolve and succeed in adapting, or will we be mapping it back to those? That'll be very interesting to see what happens there. And also, with the understanding of these, of what the best input is to these type of algorithms, are we going to go back and change the imaging protocol? So we often assess acquisition protocols based on what the RAD, they're thinking in their mind. How do I want to view this, and what do I need to see in order to come to a diagnosis, given the type of case that I'm going to be looking at, and given the type of exam we're doing? Here's what I want taken within, and this is often agreed upon within an organization. But what happens if a computer says, well, that's cool for how you look at it and how you think about it, but how I think about it and how I'm more successful looks like this? Are we actually going to start to incorporate that into the front end techniques that we do that, so that favors, makes it easier for these, or a higher accuracy rate for these type of deep learning? And then you can imagine these computers as they learn in these settings, how, when we, if I today take a study and it gets viewed and reported on and signed by the RAD, and then a month later we have some questions about that. Was it accurate, or what was the thinking behind it? We know who did it, assuming they're still around and we can find them, and assuming they can look at the case and jog their memory or whatever, they can talk about how they arrived at that. Hopefully they remember from the hundreds of cases they've looked at since then. But if a computer does it, what happens if the computer is learning? Do we have to lock down the algorithms, and how each of those algorithms are weighting the inputs, and kind of almost serial number that set of dozens and perhaps hundreds or even thousands of weightings and algorithms that it has and layers that it's using, so that we know for regulatory needs? So do we know for legal discovery? So that software was pretty smart on Monday, even smarter on Wednesday, and really smart on Friday, to use an extreme example. Is the person who, how do we determine which version of intelligence was applied, and what is realistic out of an expectation of an outcome for those? And then for research and regulatory needs, often in regulatory needs, it's very important to be able to define and designate exactly what that medical device is made up of. And the reason is if it needs a correction. So in software, it might be an update to that software. The medical device manufacturer needs to be able to produce a list to say, here's exactly all of the places where my product is installed. Here is my correction plan, which is typically applying an update, and this is exactly the library changes or whatever I'm doing, so that it can fulfill its responsibility to ensure that the product they're releasing as a medical device is safe and effective, and they can do that post-market corrections. What happens if the software isn't static in that sense? So how do we lock down and understand which exact version and thoughts process it was using? And the other thing too is I think we're going to need to have some form of tracking the performance of these algorithms. So today somebody does a study and they look at a certain type of imaging protocol for lung or liver, produce a bunch of results. This is the dose we use, this is the technique we use, and this is how it was provided more accuracy in terms of diagnosis. And then over time people start to read this and start to perhaps change what they're doing in their organization. Well, if we have a bunch of computers that are just learning at different rates and they're smart and this is happening, how do we actually compare whether your smart computer and your smart algorithms are really up to the standard of care that should be there? So even within the education process of medicine, what we taught as a standard of minimum knowledge you would have to have in the, say, 1920s compared to the 2020s is very different. So, and if you took a doctor who was educated in the 2020s and put them in today's time, transport them to today, you know, would we think that it is safe for them to be practicing medicine? I would suggest not. So how do we determine and share out the accuracy of these algorithms or sets of algorithms so we can actually quantify this and say, are we achieving a level of performance equal to humans or computer versus computer? How do we know this computer, if one computer is demonstrated to be much safer in terms of more reliable uh, diagnoses and outcomes, should we not require, or should it not be at least communicated to the providers and to the consumers that in that care setting you are using a computer that is not as accurate as others. So this gets into some of those ethical questions perhaps. So a couple last closing thoughts is there's going to be a lot of not only hype, but there's going to be a lot of breakthroughs in machine learning, not just in medicine, but everywhere else. And you're going to see, I've had debates with people whether, a pilotless plane where the ground and the airports and the landing strip and the plane itself are all well-known quantities, and the path it's supposed to take is well-known quantities. Is that more reliable to have a robot do it versus a pilot who may be drunk or be unstable? Um, if we had a locked pilot cabinet, which no one could get into, it's very difficult for someone to, take over that plane. So which is actually safer or less safe? That's one question. So you're going to find, and this is an example here of a self-driving car, over the last few years, the advances in this have been spectacular. But the first time one crashed, everybody was looking at it and kind of saying, "Oh, look at it! It's not as smart as it thinks it is." But the reality is, there are over 100,000 car accidents caused by humans a week, and as long as we're looking for machines to be perfect, and I believe over time we're going to find that really the standard is, are they as equal to or better than humans at what that task is? Um, Certainly you see industries like car manufacturing where the specificity of that weld is much more accurate with a robot than it used to be with a person. And we're going to see a lot of those advancements. And if it can do it at a lower cost, it's certainly going to be a lot of pressure to make the cultural shift to start accepting the computer for doing that. And in light of that, the one thing I think is interesting is when people say, is the machine as good or better than a person? If I was on the side of someone advocating for the use of machines, being a vendor, a researcher, or someone who would benefit from computers doing that, someone who perhaps financially, if the computer can do it for much cheaper, that's good for me. One of the things I would probably do is I would do a very large scale study to actually measure how good humans are at something. So I would take all of these imaging studies that were done by radiologists, and I would go through and track the progression of those patients through all these electronic EMRs we have now, cross-index that to find the ultimate outcome of that patient, and I would statistically generate all this information to say, are radiologists 99% accurate, 90%, 70%, 50%, and that will help me when my machine starts to approach that same threshold for those same type of problems. Obviously, there's different problems in different types of modalities and different types of patients and disease progressions. But if I start to get approach to that, that is my sales pitch to the consumers and to the world and to society in general that says, listen, I'm only at 50%, but guess what? Healthcare is 48%, if that was the case. And I think that's going to be a very telling moment, and I think it's going to be an area where there's going to be an enormous amount of debate in terms of trust. So I want to thank you for taking the time to go through this. This is just obviously probably 2 months from now there'll be all kinds of new information, but this is just kind of my thoughts and some of the things I'm been studying. If you're interested, you can contact me at dondennison.com and reach out to me, and I'd be happy to comment on or discuss this further. And I hope to see you at one of the meetings nearby. Thank you very much.